All right, next up we have acid-base indicators, and we'll also talk about titration curves today. First of all, indicators are usually weak organic acids where the acidic form, which we'll represent as HIN, that's not an L, that's an I. HIN is a different color than the basic form, which is take off the H plus, we're left with IN minus. So indicators are often used in titrations to identify the equivalence point. Now, something to keep in mind is this term equivalence point. Equivalence point refers to the reaction. At the equivalence point, you have stoichiometrically equivalent amounts of acid and base. Now, I say stoichiometrically equivalent amounts because sometimes that's not always a one-to-one ratio. Sure, in the case of a titration between hydrochloric acid and sodium hydroxide, the equivalence point occurs when you've had a one-to-one ratio of acid added to base or vice versa. But sometimes it's not the case. So we'll go with stoichiometrically equivalent amounts based on the stoichiometry of the reaction between the particular acid and base. Now, something else to be mindful of is this. When performing a titration, the most appropriate indicator that should be used is one where the endpoint, make sure you understand what this means. Endpoint is when the indicator changes color. A lot of times people use endpoint and equivalence point interchangeably. They are not interchangeable. Endpoint refers to the indicator, equivalence point refers to the reaction. So you want to pick an indicator whose endpoint is as close to the equivalence point for that titration as possible. Now this happens when the pH at the equivalence point is closest to the pKa of the indicator. Let me show you something. Let's look at the Ka for an indicator. So we have, and this equation is also written in your book, so you can see similar setup. So we have H plus and In minus over HIN. And if we have an equal amount of the HIN and IN minus, then that means the Ka of the indicator is equal to the H plus. And if we negative log that, we get pKa of the indicator is equal to the pH of the solution. So that's how that works. So there's a table of indicators. Let's get to the next slide. Figure 19.1 on page 756 and 19.2 as well. Shows 19.1 shows some different indicators, and they're different colors at different pHs. So letter A, that's methyl red, is kind of red at pH below 5. At 5 is kind of an orange, 6 kind of orange, and above 6 is yellow. Letter B, that's bromothymol blue. Bromothymol blue is yellow in acidic solution, blue in basic solution, and a neutral solution, it is green. And then, of course, our favorite indicator there shown in letter C, we have a colorless solution below pH 9. Above pH 8, above 8 is pink. That, of course, is phenolphthalein. You'll want to reference table 19.4 on page 757 for your pre-lab assignment. And some other questions also that we'll be asking today in terms of which indicator would be the most appropriate to use for a particular titration. And so we want to look at the pH at which that indicator changes color. So be careful. The pH at the equivalence points of a titration is not always 7. Be careful. Welcome to Chem 2. All right, let's take a look at titration curves. A titration curve is a graph of pH versus volume of acid or base added. So that's the substance that's in the burette, and that substance is known as the titrant. So titration curve, graph of pH versus volume of titrant. So let's label our axes. I don't have a lot of room down here, so put that volume. And let's start off with a titration between a strong acid and a strong base. So you're going to take a strong acid. This would be in your flask. So we're starting with strong acid in the flask. And then you're going to add strong base. So that's in the burette. And just for fun, let's put some values here. Let's say we have 0.1 molar HCl being titrated with 0.1 molar NaOH. So just for fun, let's go ahead and assign some values. So what is the pH of this solution before any base has been added? So go ahead and pause the video and calculate that value. pH before any base has been added. So it looks like we have 10 to the negative first is our concentration of H plus. This is a strong acid. So negative log of 10 to the negative first is 1. So the pH of the solution before any base has been added is 1. All right, so let's show what happens to the pH as you add sodium hydroxide. So pH is going to stay pretty consistent for a while. It's going to shoot up, and it's going to increase by a significant amount and then level off. So halfway up this vertical part here, so let's just say right there, this is the equivalence point. What's in this solution at the equivalence point? So again, if we look at the balance equation for the reaction, we have hydrochloric acid reacts with sodium hydroxide. What do you make? You make water and sodium chloride. So in the solution at the equivalence points, we have no acid, we have no base, right? We've completely neutralized the acid with the base. And so all we have is a solution of sodium chloride. Question, is sodium chloride an acidic, basic, or neutral salt? Holy cow, here we go with this, huh? So sodium chloride is a neutral salt. So that means then at the equivalence point of this titration, the pH is, you guessed it, 7. So of course, when you go past the equivalence point, you've added more than enough base to completely neutralize the acid. That's why your phenolphthalein is going to turn really dark. And it's going to continue going up until it reaches some maximum when it's just all sodium hydroxide in there and a whole bunch of excess. So make sure this makes sense. Let's see. We can fill that out next. So number 3, unfortunately, there's no room in your notes, so maybe draw in the margin. We're going to go the other way around. So we're going to take a strong base. So this is in your flask. And we'll go with sodium hydroxide. And you're going to titrate that with a strong acid. That's in the burette. So let's go 0.1 molar sodium hydroxide. Let's go here. Titrated with, or titrated by 0.1 molar hydrochloric acid. So let's label our axes. We got pH versus volume of titrants. Let's again do like we did last time. What is the pH of this solution before any acid has been added? Go ahead and pause the video and calculate that. So concentration of hydroxide is 0.1 molar. Negative log that, we get 1, which is the POH. Subtract that from 14 to get the pH. So we're starting this time really high, 13. All right, so let's show what happens as you add hydrochloric acid. So once again, pH is going to decrease slowly, and then it's going to shoot down and end up something like that. So again, halfway, this vertical part or nearly vertical parts, this represents when the acid has completely neutralized the base. You've added enough acid to completely neutralize the base. Again, I ask, what's in this solution at the equivalence point? How much hydrochloric acid is there? None. How much sodium hydroxide is there? None. You have stoichiometrically equivalent amounts of acid as base. So once again, we have just a solution of sodium chloride. Sodium chloride being a neutral salt, therefore the pH at the equivalence point is 7. So why is that? It says at the equivalence point the pH equals 7. This is because, of course, neither the Na plus nor the Cl minus will undergo hydrolysis. They both come from a strong acid, strong base, and so no hydrolysis occurs. The pH then at the equivalence point will be 7. So going back to page 757 in your books, what would be an appropriate indicator to use for this titration? Go ahead and pause the video and see what you come up with. All right, so we want something that changes color at 7 or very close to 7. And the best choice there would be bromethymol blue. It changes color at 7. Now we do use phenolphthalein as our indicator for this titration. Why? Well, again, look, the pH changes by quite a bit when adding just a very, very, very small amount of acid or base. And so a very small extra amount of base, let's say, according to our last titration curve, is going to result in a big change in pH. And so phenolphthalein, even though it changes color at about 9, is even okay to use for this titration as well. All right, let's take a look at the next one. All right, this time we're going to take a weak acid. So again, we're starting with that in the flask, and you're going to titrate it with a strong base. Whoops. So let's go with 0.1 molar acetic acid. And you're going to titrate that with 0.1 molar sodium hydroxide. Let's label our axes. And same again as last time. What is the pH of the solution, the 0.1 molar acetic acid, before any base has been added? This one's going to take a little bit longer, so go ahead and pause the video. And you can do it all on your calculator if you want. You don't have to set up your ice table or anything. Go ahead and pause the video, see what you get. So what'd you get? pH of the solution before any base has been added. Not 1, like last time, but a little higher than 1, about 2.87. So we're starting, let's just say we'll start right there. Graph's not to scale. And then again, let's show what happens to the pH of the solution as the sodium hydroxide is added. This one's a little bit different, kind of goes up and levels off a little bit, then increases, and then maxes out at some point. So again, about halfway up the vertical parts of this curve represents our equivalence point. What is in the solution at the equivalence point? Let's take a look at our equation for the reaction. So you make water and sodium acetate. So at the equivalence point, you have no acetic acid, you have no sodium hydroxide, you have a solution of sodium acetate. Na plus hydrolysis? No. CH3COO minus hydrolysis? Yes. And so what we're going to see here this time is that the pH at the equivalence point is greater than 7. Why? Think about it. Let's look at our hydrolysis equation. We've been talking about this. So acetate reacts with water to produce a very small amount of acetic acid, and you guessed it, hydroxide, which drives the pH up. So pH at the equivalence point greater than 7. Something to be careful of and mindful of, not really careful of, mindful of is a better term, is that in this region here, after you've added a pretty good amount of base, but well before that acid has been completely neutralized, the solution is a buffer. That's why its pH doesn't change, by very much as you continue to add more and more base. Why is it a buffer? Well, let's think about this. You've partially neutralized the acid. Any points before the equivalence point, the acid is partially neutralized. So you're going to have some of this still remaining in solution, but you're also going to be producing some acetate. So you have a solution that contains acetic acid and acetate, aka a buffer solution. Number 4, very, very, very important. Halfway through the titration, this is known as one of two things: the midpoint of the titration or the half equivalence point. Let's go back here. So if the equivalence point occurred when you added this much of the base, let's go halfway. About halfway is right there. That's our half equivalence point. What's the significance of that? At the half equivalence points, the pH of the solution is equal to the pKa of the acid being titrated. Why is that? Well, let's go here. We can do this one of two ways. I'm going to choose to use Henderson-Hasselbalch. Remember, any points before the equivalence point, this solution is a buffer. So we have, in this case, we have concentration of acetates over concentration of acetic acid for our buffer. At the half equivalence point, what is true? Let's say we have 1 mole of this to start with, and at the half equivalence point, we've added 0.5 moles of that. 0.5 moles of the base reacts with how much of the acid? 0.5. How much is left? 0.5. How much acetate is produced? 0.5. What do you notice? At the half equivalence points, the concentration of the conjugate base is the same as the concentration of the acid. So what does that mean here? If those are the same number, that equals 1. What is the log of 1? Pretty sure the log of 1 is 0. Therefore, at this point in the titration, the pH of the solution is equal to the pKa of the acid. So if we know the Ka of the acid, we can determine the pH at the equivalence point. If we know the pH at the half equivalence point, we can calculate the Ka or pKa. So this is very, very, very important. In fact, this is what we're going to do in our next experiment. We are going to determine the Ka of an acid by using something similar to what's going on here. All right, as we said, for this particular type of titration, the pH at the equivalence point is greater than 7 due to the hydrolysis of the weak acids anion, in this case acetate in our example. So take a look again, 757. Which indicator would be the best one to use for this titration? Pause the video while you find that. All right, so we want an indicator whose endpoint is above 7, something that changes color above 7. I say in this case, the best one to use would be phenolphthalein. All right, let's take a look the other way around. We have a weak base, so that's in the flask. Let's say maybe an aqueous ammonia solution, titrated with a strong acid, let's say hydrochloric acid, that's in the burette. Let's say we have 0.1 molar aqueous ammonia, and we're going to titrate that with 0.1 molar hydrochloric acid. You guessed it, calculates the pH before any acid has been added. Go ahead and pause the video and do that now. Did you get 2.87? If you did, that would be the pOH of the solution. We want pH. So pH of the solution before any acid has been added is certainly less than 13. It's about 11. So let's take a look at the pH as you add acid. We're going to get something like this. Goes down a lot, levels out. And right here is our equivalence point. This is not really drawn very well, but I think that's okay. Maybe I'll change it a little bit. Looks a little yucky. I don't know. My graph's a little squished here, so I'm gonna start up here. That's all right, I guess. All right, so there's our equivalence points. What is in the solution at the equivalence point? So let's take a look at our equation for the reaction. We end up producing ammonium chloride. So at the equivalence point, there is no ammonia, there is no hydrochloric acid. We have just a solution because both of these are in solution here. So we have a solution of ammonium chloride. Is ammonium chloride an acidic, basic, or neutral salt? Oh boy, here we go again. Cl minus, no hydrolysis. NH4 plus, hydrolysis. So hydrolysis of ammonium produces a little bit of ammonia and some hydronium, which means that the pH at the equivalence point is going to be less than 7. Once again, in this region here, we have a buffer. Why? Well, again, if we have, let's say we have 1 mole of ammonia and we add, just some hydrochloric acid, we're going to end up still with some of this left in solution and some ammonium, the conjugate acid of ammonia. If you have both in solution, it is a buffer. All right, so we see this time because we have an acidic salt at the equivalence point, the pH at the equivalence point will be less than 7. This time, what indicator would be the best one to use? Go ahead and pause the video and find that. All right, we want something that has an endpoint that is less than 7. We don't know exactly. I mean, we can calculate, and you will later, the pH at the equivalence point. So we'll just estimate it's either methyl orange if it's really low, or even methyl red if it's just a little below 7. So it just depends on your concentration and what acid and what base you're using. Once again, we can go, let's see, here's equivalence point. So about right here is half equivalence point. At the half equivalence points, we can use that to find something. So again, here this time, POH equals PKB plus log of, in this case, NH4 plus over NH3. And at the half equivalence point, this is equal to 1. Log of 1 is 0. So at the half equivalence points, the POH, notice we're measuring pH here though, the POH of the solution is equal to PKB. So you have to get this pH here, subtract that from 14. That's your POH, and then that would be equal to the PKB, which you can then anti-log to find the KB for the base. All right, so there's a really good table on page 766. It goes over, it is not on 766. It's on page 763. Sorry, I was looking at 2 different numbers there. Table on page 763 goes over a lot of the stuff we talked about in this unit. It summarizes a lot of things, and so take a look there. It's really, really, really helpful. It's got everything we talked about all in one place. All right, let's take a look at an example. I know this is not in your notes, but you can add this maybe to the back page. We're going to do a couple on that back page there. We'll start off with an easy one that we can do together kind of, and then I'll give you the hard ones to do by yourself. So take a look at number 52. It says a 22.0 milliliter sample of 0.145 molar hydrochloric acid solution is titrated with 0.106 molar sodium hydroxide. Calculate the pH of the solution before the addition of any NaOH and after the addition of 11.10 milliliters, after the addition of 24.0, 41.0, 54.4, 63.6 milliliters. So let me walk you through that setup. First thing you want to do is write the balance equation for the reaction. You could, I suppose, write a net ionic, but I'm going to write the whole thing here. And luckily, this reaction produces a neutral salt, so we don't have to take into consideration any hydrolysis that may occur. So we need to determine the pH based on how much acid remains in the solution if it's before the equivalence point, or how much just base is in the solution after the equivalence point. So we're going to go to our good old SCAR table. Remember, when using a SCAR table, we want the amounts in moles. So let's start off with calculating the amounts in moles of hydrochloric acid that we start off with. Go ahead and pause the video and find that number. Calculate that number. All right, so this is, I probably should have written HCl plus NaOH, but that's fine. If you want to switch that, that's okay. So this is the number of millimoles. So I just took the molarity and multiplied by milliliters to get millimoles. We don't need it for letter A though. So we want the concentration, or sorry, the pH of the solution before the addition of any base. Go ahead and find that number, please. Pause and do that now. All right, so what did you get? So letter A, we have a pH of, I think it's 0.84. So we take negative log of 0.145. Since it's a strong acid, its H plus concentration is the same as the concentration of the acid. So log of 0.145 is negative log of 0.145 is 0.84. All right, letter B. Now we're going to add some sodium hydroxide. All right, so let's start off with this. How much in millimoles sodium hydroxide are we adding? So we're adding 11.10 milliliters, and the concentration of that is 0.106. So we have 1.18 millimoles of NaOH. So what do you notice? Where are we at in the titration? We are before the equivalence point. So that means that the sodium hydroxide is our limiting reactant. And again, yeah, we can put this if you want, but since this is a neutral salt, will have no impact on the pH of the solution. So I really don't care about the amount of NaCl in this problem. If you produce an acidic or basic salt, then we have to take a look at that. So go ahead and calculate the amount of millimoles of HCl that remain in the solution. Do that now. I think I can do that one in my head. So that's 2.01. Again, that's millimoles. And we want to find the pH, so we need to know the concentration of the HCl solution. So we're going to take the amount in millimoles and divide by the total volume. So we start off with 22 milliliters of hydrochloric acid, and to that we added 11.10 for a total of 33.10 milliliters. So we can take the amount of millimoles divided by milliliters, and we'll get our molarity. So it looks like we have 0.0600 molar, and we negative log that, and that will give us our pH. So notice that the pH went up. Of course it did. You're adding a base, you're using up acid, the pH is going to go up. All right, let's take a look at letter C. Let's clear our board here. We want to keep that same amount. All right, so this time, go ahead and calculate millimoles of base added. We're on letter C, 24 milliliters. Go ahead and pause the video and see how many millimoles that is. All right, so this time we have 2.54. We are still where? We are still before the equivalence point. So how much HCl remains in the solution? We have 0.65 millimoles. And again, we want to find the concentration of HCl, so we're going to divide by the total volume. So once again, that was 22 milliliters of HCl, plus we added 24 milliliters of the NaOH. And that gives us a total volume of 48 milliliters. And I believe we end up with, what do we end up with here? 0.010 molar for the concentration of HCl in the resulting solution after you've added 24 milliliters of base. So we'll negative log that. I can do that in my, almost do that in my head. Actually, yeah, what's going on here? Let me take a look. Ooh, I must be getting tired. I got to back up a little bit. I'm neglecting my significant figures here. So letter B, I think that's 1.217. I think we want more than just that many significant figures. 1.217. That sounds better. And then our first one technically should be 0.839. Since we had concentration had 3 sig figs. So our pH then will have 3 digits after the decimal. Sorry about that. And then here I'm having apparently a calculator error. So 0.65 millimoles over 46 total milliliters. We have a concentration of 0.014. Does that sound about right? And so if we take the negative log of that, we will get the pH at that point in the titration, which happens to be, let's see if I can do this right this time, 2 sig figs, so we want 2 digits after the decimal, 1.85. All right, letter D, let's clear the board again. So this time, how much of the base have we added? We've added 41 milliliters. So calculate the number of millimoles. And this time we have, is that right? 4.35? Looks like it. I wish we did one at the equivalence point, but they don't have a volume that gives us at the equivalence point. Well, that one's pretty easy though. At the equivalence point, we know the pH is going to be 7. So this time we are past the equivalence point. We added more than enough base to completely neutralize the acid. So this time the hydrochloric acid is our limiting reactant. And we have excess base in solution. How much? Looks like 1.16 millimoles. Take that divided by the total volume. Again, we had 22 milliliters of hydrochloric acid. We added 41 milliliters of our base, so 63.0 milliliters. And let's see what the concentration of the sodium hydroxide is. So it looks like, how many sig figs? We want 3 sig figs, 0.0184 is the concentration of the sodium hydroxide. Whoops. Let's try negative log of that. That's going to give us the POH, and we want the pH. So the pH at this point, according to the book, is 12.265. I think I did that right. Let's make sure. 0.0184. Yeah, we got some. I'm having some serious calculator issues here. I don't know why. There we go. 12.265. Sounds about right. All right, letter E and letter F are just adding more and more base. You're going to be past the equivalence point, so you'd have the same type of setup as what we have here. So I think I'm going to stop there because it's been long enough, and I'm going to go home. All right, thanks for watching. You guys have a great day.